Alright, so in this video I'm going to start to talk about electrical force. In the previous topic we learned about electrical charge, how objects became charged, and then we started to look into how charges interacted with one another. And based on our experimentation, we realized that opposite charges attract and like charges repel one another. Well, the attraction and repulsion between electrical charges is actually an electrical force. Now, electrical force is a force that can be exerted without two objects coming in contact with one another, and that is called a field force. And we've already looked at one field force this year and performed some calculations with that, and that was the universal law of gravitation. So that gravity is exerted through space without two objects needing to come into contact with one another. And so if we recall the equation for that field force, it'll help us to remember or understand this new equation for electrical field forces. So remember that the force due to gravity is equal to G, which was the big gravitational constant, and then m1 times m2, so the masses of the two objects made, the bigger the mass, the stronger the gravitational force, and then how far apart they are away from each other, or r squared here, the distance also affected. So the closer they're together, the stronger the force, or the further they are away, the weaker the force. And remember that this is squared on the bottom, so distance is really kind of more important in determining magnitude of force than the mass is. And this is actually called an inverse square law because of the square on the bottom there. Now, the electrical field force is also an inverse square law. And if we look at the equation for electrical force, it'll look nearly identical to the gravitational field force. So here is the equation for electrical force. We have force electric is equal to K. K is also a constant. I'll give you that value here in a second. But it's equal to Q1 times Q2, which is the magnitude of the charges, so similar to like the size up here, divided by r squared, how far away they are from one another. So it's almost identical to our gravitational field force. Now, the K in this equation is Coulomb's constant. And Coulomb's constant is this, 9 times 10 to the 9th newtons over meter, or newtons meters squared over Coulomb squared. So notice if I put that unit in up here, the meter squared is going to make the r unit cancel out, and the Coulomb squared makes the c's cancel out. So we're left with newtons. Now remember, on your reference table there's a bunch of different constants, so we can see here we've got big G, the gravitational constant, right here, but we also have Coulomb's law constant, which is right here, 9 times 10 to the 9th with the variable. So if you forget it, you know that you have it in your reference tables. Alright, so let's go ahead and actually do a practice problem using Coulomb's law. So let's say that we have a nucleus of an atom, and within the nucleus of the atom there are 3 protons. And we want to know what is the electrical force between the nucleus of the atom and one of the electrons that's 2 times 10 to the negative 6 meters away. So this is a really practical application of this problem, and if we're able to quantify this force, then it would tell us the location of electron in an atom, which is sort of important for us in terms of chemistry and understanding how atoms work. So what we're going to do is we're going to have our nucleus here that's going to have 3 protons. Some distance away over here, you're going to have an electron. Okay. Now, you have positive charge and you have negative charge, so this is an attractive force. And if we wanted to, if we oriented it like this, remember if we're dealing with forces, we're always going to put ourselves in the position of one of the charges. So in this case, if we were wondering, what is the direction of the force on this, or on the electron relative to the protons? Well, the force on the electron, we draw the free body diagram, would be the electron, and it would want to move in this direction. Alright, so let's just calculate the magnitude of that force. We know the direction of it, so whether or not it's positive or negative isn't really going to matter here. So we've got Fe equals K Q1 Q2 all over R squared. Right? So Fe, I know that K is 9 times 10 to the 9th from my reference tables. And then I'm also going to look and see, all right, one of the Q's are my 3 protons. So if we look here on the reference table, again, remember we have the charge of, it says elementary charge, which is a proton or an electron. So it's 1.6 times 10 to the negative 19th. So in order to get that, to calculate for 3, we just got to multiply it by 3, and I get 4.8 times 10 to the negative 19th. So that's the first charge. And then I get Q2, which is going to be just 1 electron, so 1.6 times 10 to the negative 19th. And then all over R squared, which I said the distance apart was 2 times 10 to the negative 6th squared. Okay. Now, what I like to do is, just so that I don't mess up on my calculator and not use my parentheses right or something like this, is I'm going to plug this in first and just record it to make it easier. So let's do 2e to the negative 6, and let's insert some parentheses here. And I'm going to square that. So I'll get 4 times 10 to the negative 12th. So then I can just go ahead and punch in all my numbers. So 9e to the 9th times 4.8, so e to the negative 19th times 1.6 e to the negative 19th, and then divided by 4, so I can e to the negative 12. And I get this. So the force in newtons between this proton, these protons in the nucleus, and the electron is 1.73 times 10 to the negative 16th newtons. Right? And we already know the direction because it is to the left. Now, one more thing that I want to mention about electrical force is, remember that electrical force is a vector. So forces could be added to one another just dependent on where they are. Okay, so let's say that I go ahead and I put I've got the same scenario, I've got these 3 protons, and if I have this electron here, and I put another atom over here, and let's say they're sharing the electrons, and there's 3 protons there, then I would have a force, this electron would be in equilibrium because I would have a force in this direction and a force in this direction, given that the distances were the same, equivalent to one another. So the net force on this would be equal to 0. So remember that we're adding vectors as well, and to keep in mind that if there's more than one force, then we will have to apply some vector addition. But for our purposes, it will always be something very simple where we're either just going right and left or up and down. We won't have to go back and do our vectors at angles for these instances. All right, so that is electrical force.